The second slide on Charles' law relates the law with respect to absolute zero temperature. In other words, a clear understanding and interpretation of Charles' law leads us to an interesting speculation about the lowest temperature that one could achieve. And this actually turns out to be very profound and important in physical chemistry. For example, if we take this plot that we've seen in the previous slide of Charles' law, where we're plotting V versus T with a blue straight line, and if I were to now extrapolate that to hit the x-axis, and it's cutting the temperature axis at some certain value that is well below zero. Now note that the temperature is centigrade. So below 0 degrees centigrade, the blue line cuts the x-axis. And obviously the volume of the gas at this temperature should have diminished to 0 at this temperature. And below this temperature, the volume actually should become negative, which is not possible. And so this is an interesting case for Charles' law extrapolation. And so let's analyze this in more detail, what's going to happen here. So we write our linear expression V equals to V0 plus dou V by dou Tp multiplied by temperature. The temperature is still expressed in degrees centigrade. V0 is our intercept on the y-axis, and dou V by dou Tp is the rate of change of volume with respect to temperature at constant pressure, or in other words, the slope of the straight line that is shown on the right. Now, it has been noted that experimentally, the value of 1 over V0 multiplied by dou V by dou Tp is a constant for almost all gases that people have measured, and within a rough value. And it turns out to be 1 over 273.15. And this is given a special symbol, alpha 0. And so alpha meaning some sort of a constant that's intrinsic to the gas properties. So now we can rearrange this equation that we have written on the left using alpha 0 for the slope of the line. So in other words, rewriting this equation, we will see V equals to V0 plus V0 multiplied by alpha 0 multiplied by T. That's because the relationship between alpha 0 and V0 are used from the above to rearrange and replace the derivative dou V by dou Tp. Now we can pull out V0 and alpha 0 from both the terms and write this as a product. And that's equal to V0 alpha 0 multiplied by, in the parenthesis, 1 over alpha 0 plus T. Now the reason to write it this way is now that I can replace the value of 1 over alpha 0 with 273.15. So if I do that, V equals to V0 alpha 0, 273.15 plus T. 273.15 being a constant, we can now replace the quantity in the parenthesis by a new symbol, capital T, where the capital T is equal to 273.15 plus T degrees centigrade. So we refer to this as the Kelvin scale of temperature. So numerically, it is offset by 273.15. And so coming back to the plot on the top right-hand side, we now conclude that in terms of x-axis written in degrees centigrade, the blue line should cut the x-axis at minus 273.15 degrees centigrade, or we can redefine this as equal to 0 Kelvin. And 0 Kelvin being the absolute zero temperature. Why is that? Because your thermometer, in this case air thermometer, could not measure possibly values uh, at this temperature, 0 Kelvin or below, because the volume will diminish to 0 at this temperature and expected to decrease further after that. So since that is an impossibility, Kelvin has concluded that this is the lowest temperature that is ever attainable.